Good morning, everyone. So very privileged to deliver this presentation. So the title of it is called Exploring Leray's Formulation of the Navier-Stokes Equations. And I want to make a comment first. This is really basic, fundamental, and rudimentary stuff. So I hope you'll enjoy it, and I hope you'll find it easy to understand. And let's hit the ground running. Let's first of all talk about the history of the so-called Navier-Stokes equations. That's really basic stuff. So the Navier-Stokes equations have a rich history that spans the fields of mathematics and physics, reflecting significant contributions from numerous scholars over the centuries. So let's start with the early foundations. The foundational aspects of fluid motion trace back to Sir Isaac Newton, his laws of motion and his theory of viscosity, which were documented in the late 17th century. However, it wasn't until the 19th century that these ideas were rigorously applied to fluid dynamics. And then the first name in the name of Navier-Stokes equations is Claude Louis Navier, who was an engineer and physicist who made pioneering contributions to the theory of fluid dynamics. And in the year of 1822, let's write this year here, 1822, when he was only 26 years old, the same age as I am now, he developed a set of equations, later known as the Navier-Stokes equations, that describe the motion of viscous fluids by extending Euler's equations, which were suitable for inviscid fluids. And the third person, actually the second person in the name of Navier-Stokes equations is George Gabriel Stokes, who was another mathematician and physicist. And in the year 1845, that is a few years after Navier developed this set of equations, Stokes rederived the motion equations by including continuity equations for incompressible flows and further refining the role of viscosity. And so I believe Stokes is no stranger to us because I believe most of you have heard of this theorem or have taught this theorem in some courses called Stokes' theorem. But the fun fact is Stokes wasn't the one who first discovered this theorem. He learned this theorem from a letter by his friend, another mathematician called Lord Kelvin. And he wasn't even the one who first published this theorem. He included this theorem in an exam he gave to his students at Cambridge University. I'm not sure how many of his students ended up doing that correctly, but that's what he did. And in fact, Stokes held a pretty prestigious position known as the Lucasian Professor of Mathematics at Cambridge, and this chair has a storied history with famous holders, including Sir Isaac Newton, the one that the mathematician we just introduced above, and much later, Stephen Hawking. So that's it. So let's dive right into the heart of the matter today, which we call Act 1. So I've broken down today's topic into 4 acts. Let's start with the first act, that is to get to know the main character today, the Navier-Stokes equations of incompressible flows. So that's what the set of equations says. The first equation says the material derivative, which is denoted as d over dt, of this fluid velocity v equals the right side, which is negative gradient of p, where p means the scalar pressure plus a constant, which we call the kinematic constant of viscosity, which is greater than or equal to 0, times the Laplacian of this fluid velocity v. So that's what the first equation says. And also the second equation says the divergence of v equals 0. And this condition has a name, which we call the circle 1. That is, in general, if a flow is volume preserving, we call it incompressible. This definition speaks volumes. That is, we have a corresponding proposition which says if a flow is incompressible, the divergence must be 0, which is precisely what this second equation says. So if this v, so this, in other words, this equation just means that this fluid velocity v is incompressible. Does that make sense? So that's everything. And another remark I'd like to make is that there's another form of this Navier-Stokes of the set of equations. That is, if we first compute this material derivative, that is, if we expand or unravel the definition of it, and then use V to hit it, after this material derivative, we're going to get another form of this first equation, which we call parenthesis 1.1 prime. This is probably a form familiar to most of you, another more commonly seen form. And of course, they're equivalent. In particular, and also another remark in particular, if we let this V be zero, the original Navier-Stokes equations will boil down to this new form, that is the material derivative equals negative gradient of P. Sometimes we add another vector field G, which we call the body accelerations acting on the continuum, for example, the gravity acceleration. And we call this new set of equations the Euler equations in fluid dynamics. So before we move on, do you have comments or anything to clarify? All right, so let's go to Act 2. This is another pretty deep topic that is about solutions to this set of equations. So let's briefly introduce this proposition 1.5, because we're going to have to use the proof when we introduce the main proof of the main character, the Leray formulation today. And so let's first of all read this proposition together. We let this D of T be a real symmetric 3x3 matrix with a trace equal to 0. Determine the vorticity, which is defined this way. That is, the vorticity is defined as the curl operator of a vector field V in general. And given on that condition, this proposition says we have the two solutions to this set of equations. That is, the velocity field V equals this guy, and the pressure scalar equals this guy. And they're exact solutions to the 3D version of the Navier-Stokes equations. So this proposition provides explicit solutions to the 3D Euler and Navier-Stokes equations for incompressible flow under certain conditions. So for the proof, let's briefly introduce just the first two lines. For the rest, we don't have time to introduce them, but you can see this textbook, which is the book I'm following today. And first of all, let's compute let's start with the general form. That is the one we just introduced above, parenthesis 1.1. If we derive both sides, if we differentiate on both sides with respect to xk, we're going to end up with the first equation here. And then motivated by the fact that we want to sort of integrate everything or encompass everything into one logical whole, we can introduce the two actually matrix notations, V, capital V and capital P. So we can rewrite the first equation as the second 1.29 this way. Notice d over dt is still the previously introduced material derivative, where the first two terms correspond to this term. So this equation will be worth its weight in gold later on. We're going to have to use that. And what's noteworthy is the 3D version of the solutions to Navier-Stokes equations. This topic is included by the Clay Mathematics Institute as one of the 7 Millennium Prize problems. So that's the prize problem statement. Whoever can prove this statement will earn $1 million. So this is a real rule, a real gem. First of all, I'll give a counterexample of the following statement. In 3D, in 3 dimensions, do smooth and globally defined solutions for the Navier-Stokes equations always exist? So that's the question. You can take a look at. All right, so next, let's go to the third act. That is, let's get to the heart of the matter. Let's start deriving Leray's formulation. Let's start with the last equation we just introduced, that is 1.29. And let's build our work upon it. First of all, let's take the trace operator. Let's trace both sides to get this second equation. That is, of course, we can exchange the order of the material derivative and the trace operator. to get the second equation. And by the definition of divergence, the trace of capital V, which is defined this way, this matrix, is equal to the divergence of the velocity fluid field, lowercase v. And likewise, this trace is also the divergence. If you're not convinced, you can spell out the definition of the matrix V, you're going to end up with the divergence, which is defined as the dot product. And also, likewise, the trace of the second matrix, scalar matrix P, is the Laplacian of the lowercase pressure P. All right, so what does that tell us? That tells us that the material derivative of this guy, divergence of V, equals that. I just basically did nothing but copy the entire equation in aqua. This color is called aqua. Let's use the name of this color. All right, so by this circle 1 above, because V has incompressible flow, what does that mean? That means the divergence must be equal to 0, right? So we can further simplify this equation as the last form, that is the first term will vanish. The last term on the right side will also vanish. So that's it. And also let me mention that by definition, the velocity squared, this capital, actually the capital matrix V squared by definition is the gradient of lowercase v squared. That is this one. In other words, the gradient of P equals negative trace lambda V squared. So we call this 1.84, as followed the textbook number. And by this lemma, that is the general result for Poisson equations. If in general, if U, for example, in this case, U corresponds to P, but in general, if U is the solution to the Poisson equation, delta U equals F, with delta U vanishing as the radius approaching infinity, we have the solution is given by this equation 1.86. And it's defined this way. So let's directly take that for granted and use this theorem, use this lemma to see where this will lead us. So by this lemma 1.6, we can solve this equation for P, so we're going to get P equals this integral. I basically just copied the result of the theorem because, as you can see, this equation fits perfectly, right? With this theorem, it fits like a glove. They're on the same wavelength, so I can directly make use of this result. And with a few substitutions, so we're going to get this result. I just basically replaced a few numbers here. So the next step, motivated by this lemma, let's first differentiate under the integral to compute the gradient of P. That is, we take the gradient operator of both sides, we're going to get this. That is just by the chain rule. And then we put this constant outside, we're going to get this. And for simplicity, let's call this amber part, or this orange part, C sub n, which is another constant dependent on this another constant n. In other words, we get this equation from the textbook. After calling the Cn. And then let's combine this result with this 1.82, which is also the first equation we introduced, 1.1, the Navier-Stokes, the first equation in the Navier-Stokes equations. So let's combine them together. That is, we plug in this del P, actually this nabla P, to the second equation. So we're going to get this. The left side of the second equation equals, this result plus the second term. And then don't forget to add, don't leave out the second condition. The V is incompressible. That is, the divergence equals 0. So let's combine them together. Notice this is the second equation in the Navier-Stokes equations, right? 1.2. So let's combine them together. That is, now what we have concluded is that we've known solving the Navier-Stokes equations is equivalent to solving the evolution equation dV over dt equals that, together with the other equation, divergence of V equals 0. We just copied this result from above, because based on our work above, we've shown that they are equivalent. So we've almost seen the light at the end of the tunnel. The next result, the next step is that we somehow want to drop this 1.83, the divergence of v equal to 0, because we like simplicity. Simplicity is the utmost sophistication. So we want to somehow drop the second equation. That is the last act, act 4. We want to drop incompressibility. The motivation is, as I described, we want to drop that. So how do we do that? Well, first of all, let's prove the uniqueness. That is, let's first deduce that if the initial divergence equals 0, then for all time, the divergence must also be 0. So that's our motivation. Let's try to do that. Let's start with the first equation, 1.89. And 1.89 here. Let's div both sides, take the divergence of both sides. We're gonna get the divergence of the left side equals the divergence of the right side. And of course, we can exchange the order to get this, and we can put this divergence inside. And by the previous result, 1.84, that is this box here, we can replace this Laplacian with this negative trace as we're doing here. Actually, the other way around, we can replace the first with the second. And so by the divergence theorem, which we're going to introduce in a second, we're going to get the first term will vanish. So what's remaining is just this, the left side equals the second term on the right side. And then let's follow our motivation and intuition. We want to show the uniqueness of this equation. That is, if initially the divergence at the initial time V naught is equal to 0, then we want to show for all time somehow the divergence is also equal to 0. So just follow the general, the definition of uniqueness. We follow the definition. That is, suppose this equation has two scalar solutions. We want to show that the two scalar equations solutions are the same, right? That's what uniqueness means. All right, so let's suppose that this equation has two scalar solutions. So what does that mean? That means we set the divergence operator because it appears twice. We want to somehow integrate them. We let this divergence of the divergence of V be U. So let's call the two different solutions U1 and U2, each satisfying this equation. Notice this is obtained by unraveling the material derivative d over dt, just by the definition of this operator. All right, let's call the equation circle J, that is where J is equal to 1, 2. So let's perform circle 1 minus circle 2, that is, we substitute U1 minus U2 into this circle J, because circle J, of course, holds true for both 1 and 2. So we get the second equation. And then just by algebra, we multiply both sides by U1 minus U2, we can get this. And then we integrate both sides to conclude the integral version of the equation. And by the chain rule, the first term equals the derivative of that. Actually, by applying the chain rule backwards, we're going to get this equals that. And also by the chain rule again, the second term equals this integral. Because of course, you can see that from bottom to the top, right? If you differentiate this integral, you're going to get this square function equals 2 times this derivative. And then we pull this constant outside. So we end up with this equation here. The next step is probably the most difficult, most challenging step. That is, we apply the following general result, which we call circle 3. In general, before that, our motivation is we want to somehow further simplify them. And we want to give this right-hand side an upper bound. That is our motivation. In order to do that, we somehow want to manipulate that. So by this circle 3, in general, for a function f, defined this way, g likewise, the x derivative of the product by the product rule equals the first times derivative, the second plus derivative, the second times the first, right? Or the other way around. So, and then if we take the divergence of both sides, starting from that, we're going to end up with this equation just by the definition of the divergence, the dot product. So it equals this sum. Actually, we're following Einstein's notation. This means the sum of all the derivatives here. We just applied this. We just applied the definition of the dot product actually here. And then we use the first result here to further expand this derivative of the function, xj's derivative of the function, by using the product rule. We're going to get this. And then by definition, that's nothing but the divergence of g plus f times the gradient of g. So that's it. And then let's integrate both sides. We're gonna end up with this integral form, that is the integral of the left equals the right, where the first term in the right on the right-hand side can be written as this limit, where r approaches infinity, because this integral is over the entire Euclidean domain, Rn, right? So we can think of that as a limit, where we integrate that function over a ball of radius r, and then we let this r approach infinity. So by the divergence theorem here, we can rewrite this integral that we're taking the limit of as the bottom integral here. We're basically using this general result from calculus, the most basic version of the divergence theorem. That is the divergence of the integral of a divergence of a function equals the integral of this dot product, vector field times ds. So here we're directly using this result here. In this case, capital F corresponds to this Fg. And if in addition, we assume that either F or G, the two one of the functions vanishes sufficiently rapidly as the radius approaches infinity, then this result is nothing but zero, right? Because by definition, if Fg vanishes when r approaches infinity, then this limit must be equal to zero, because the function we're taking the limit of approaches zero as r approaches infinity. And so what we finally conclude is this result. The left side equals only the second term on the right side. Therefore, that's what this circle 2 says. We plug in this circle 2 to this original result. Let's go back to the drawing board. That is, the first term now equals, by this circle, actually circle 3 equals that, with F replaced by V in the general formula I just showed you, and G replaced by the squared sum, actually squared difference. We're going to get that. Likewise, if you replace F with this gradient, replace G with this difference, we're going to get the second term. Notice in the second equation, the second step, we're using this circle 3 backwards. That is, the right side equals the left side. It's really basic stuff, algebra. It makes sense here. All right, so what's next? The next step is so first of all, let's copy this again. Let's go back to the basics. That is, our original motivation is that we want to give the entire right side an upper bound. So now we have ended up with this form. And by definition, this constant, this kinematic constant, viscosity is greater than or equal to 0, right? Based on our definition. So in other words, and also the integrand is something squared, which is also non-negative. In other words, the entire second term, except for the minus sign, is positive. In other words, the entire second term is entire second term is non-positive, right? So we can give the entire difference an upper bound. We can directly drop this positive term because something minus a positive term must be smaller. And we also can bound this divergence of V by C by our assumption here. So I've ended up with this improvement. All right, next, let's sort of try to solve this differential inequality. Let's set this y of t to be equal to this integral. That is the left side integral. That is, now we can rewrite this inequality as 1/2 times dy over dt less than or equal to c times y, right? This is also y. And then we integrate both sides to get this, because it preserves inequality. And then we just go through the motions and solve this differential equation, ordinary differential equation, and then take the exponential. We're going to get this. In other words, we get the final result in the textbook here in this set of equations. So what does that tell us? The significance is that based on this inequality, if U1 and UV are the same at the initial time t equals 0, then they must be always equal at any later time t. That is to say, we have shown for smooth solutions, if the difference is identically equal to 0 at the initial time, then they must be identically equal to 0 for all time. That's it. That shows uniqueness. Again, because if the right side is equal to 0, then the left side must also be equal to 0 because both sides are non-negative. So we can reframe this result as this lemma 1.13. In other words, we just restated this lemma here, restated our previous result here. That is actually the proof of 1.13 in the textbook. All right, so finally, somebody wrote a poem that's really this motivated by the uniqueness. In the dance of solutions, one leads the way. Should another join, they move as one in perfect array. In the heart of math, where truths entwine, the uniqueness stands, eternally divine. I showed this to my students in discussion, actually. I wrote this. All right, so finally, the final.
Also, is that what you wrote?
I wrote this.
This is what your poem.
My poem, yeah.
Oh.
Hope it'll spice up things a little. So what does that mean? That means if the initial divergence is equal to 0, then the uniqueness tells us it must remain 0 for all time. So the incompressibility constraint can be safely dropped without hurting the diversity. And so we finally conclude that we can drop this 1.83 and remove it from the set of 2 equations to finally get this formulation. That's it. So that's all I prepared.
Thank you.